Good afternoon, everyone. I welcome you all back for the session. Now I request Mr. N. Kirtivarman, Assistant Professor, Department of Mechanical Engineering, Kingston Engineering College, to introduce our keynote speaker, Dr. E Anil Kumar.
Yes, thank you. It is a great honor for me to introduce and welcome the speaker for this session to Dr. E Anil Kumar. He is currently working as professor in the Department of Mechanical Engineering and Dean Sponsored Research and Consultancy at IIT-Tirupathi. He obtained his PhD degree from the Department of Mechanical Engineering, IIT Madras. Later, he worked as assistant professor and associate professor in the discipline of mechanical engineering at IIT Indore. He also served the institute as associate dean of academic affairs. He is founding head of the mechanical engineering departments at two IITs, that is IIT Indore and IIT Tirupati. His research interests are measurement of thermodynamic and thermophysical properties of solid-state hydrogen storage materials, thermal energy storage, carbon dioxide capture and absorption heating and cooling systems. He has published more than 100 papers in peer-reviewed international journals and proceedings of international and national conferences. Currently, he is handling 6 sponsored research products worth rupees 4 crores and some are in pipeline. He gave invited talks at many international conferences and symposiums abroad. He is editorial board member of Wiley Journal Energy Storage. He is a member of Project Review Committee for Technology Missions Division, Department of Science and Technology, India. He has reviewed more than 200 journal articles for eminent journals from Elsevier, Springer, Wiley, Taylor and Francis, etc. He is serving as a member of Board of Studies and Board of Research for many autonomous engineering institutions. Once again, I welcome you, sir. Thank you.
Thank you, sir. Thank you for your nice introduction. First of all, I would like to thank the organizing committee, especially Professor Shankar Ganeshan, for inviting me to deliver this lecture.
Thank you, sir.
Can you see my presentation, sir?
Yes, sir. Yes.
Okay, you can see my presentation now in full slide mode.
Yes, sir.
Yeah. Okay. Okay. Thank you very much. Actually, I'm not an expert of this topic, Exergy or Exergy analysis of the power systems or refrigeration systems. But however, out of interest, whenever Professor Ganeshan has asked me to deliver a lecture, I accepted it. But probably I should have asked the slot of my presentation, because after so many slots, again, I'm going to give a introductory kind of thing to this thermodynamic analysis of Exergy analysis of thermodynamic systems. But however, I feel that the approach will be different by each faculty. Some of the earlier faculty might have given the introduction about the second law of thermodynamics and Exergy analysis, especially Professor Sudapta Day and Professor Gupta Garu. Professor Gupta Garu was my MTech guide. I did my project from him. And of course, Vellore also is like a second home to me, because I did my undergraduation from Vellore Engineering College at that time. Now it is VIT. So I have a special place for Vellore in my heart. Okay, coming to this presentation. So you can hear me clearly, right, sir?
Yes, sir. Kindly proceed.
Yeah. Coming to the presentation, again, I am going to give a outline of if you want to do the Exergy analysis of any system, especially we see the systems with respect to thermodynamic point of view, being a mechanical engineer, what is the approach that we will take, and how we can do this analysis, and what kind of equations will help us. So that is the motive of this presentation. But however, since it's a very basic topic, we are towards the end of this course. Maybe by tomorrow we are going to end this course on Exergy. So I thought of introducing some combined power generation systems, where hydrogen is going to play a vital role for storing the energy intermittently, okay, especially for renewable energies. Then I would like to cover a little bit about the hydrogen storage or energy storage and its emphasis in where it comes into picture when you want to integrate the multiple types of renewable energy systems. Thanks to Srinivas Garu, morning he has already dealt with some of the basics, which is the only lecture I could able to listen in this FDP. Though I would like to listen all the lectures, but couldn't find time to listen all the lectures. But he has given some introduction about the multi energy systems, especially solar and biomass. That what I can remember exactly, and some other systems where the integration can take place between power systems and cooling systems. Okay, so with this objective, I will keep my introduction very small, because we all know that we majorly dependent on fossil fuel based energy systems, either for electrical energy consumption for industries or domestic usage, or for transportation applications. We use majorly for electricity production, we are using coal or natural gas, and for transportation, we are using petroleum based products and natural gas. So most of all these are fossil fuels, and we are burning carbon by taking under the earth and we are releasing into the environment. That is causing the global warming. It is a major concern for the human beings. And you might have seen the news articles for the last 2-3 days also in the newspapers that the Hindu Ocean is getting heated up, and there is an article yesterday saying that by 2100 many cities will be 11 cities will be under the sea, so will be submerged under the sea. So there is a great demand to reduce the carbon emissions. So to reduce the carbon emissions, we have to reduce the usage of these fossil fuels. One way of doing it is increasing the efficiencies of the conventional fuel systems, or we have to move towards the renewable energy systems. Of course, the increase in the efficiencies of the conventional systems are happening for the last 150 years or more than that. Basically, the component design has improved a lot, and the basic thermodynamic cycles, the improvement has been achieved. For example, the initial component efficiencies are very low for the compressor and turbine, or all the heat exchanging components and other accessory components. But over a period of time, understanding the process and material development has led to utilization of better materials to withstand high temperatures, as well as we introduced multi-stage expansion with reheating and multi-stage compression with intercooling in between. With all these introducing all these processes and water heaters in case of the steam power plants, all this has significantly increased the efficiency of the conventional power plants. Okay. And we are moving from single generation to cogeneration, tri-generation, and extra. But however, this may not be sufficient to reduce the CO2 emissions in the coming decade, because we also signed the Paris Agreement to reduce the CO2 emissions. So we have to still improve the efficiencies of the power plants. So that may be possible by understanding where more irreversibilities are there, where we are a lot of losses are there. So that is possible by doing second law analysis. So that way, the Exergy analysis or second law analysis is going to play a key role in analyzing the existing conventional power cycles or new power cycle, whatever we are going to propose to improve the efficiency of this power generation, either for different applications, either for electricity or for transportation, etc. Okay, so in that way, I would like to appreciate for choosing this topic for as a FDP program, and where it doesn't require much of the infrastructure. If you have a good computer, that itself is sufficient to analyze the process theoretically and identify where are the maximum losses are there. And towards moving towards the renewable energy sources, the major challenge is their intermittency. Whether you take solar or wind, or availability of biomass, these are the challenges, and the conventional efficiencies of the systems itself is a challenge. So the major problem what we are going to face is how to integrate. Of course, there is a significant improvement in the energy conversion efficiencies of these systems, either solar or wind. But still, we need to develop more technologies, how to integrate them for for smooth operating of the end users, or how to store this energy. So storing energy is going to play a vital role in integrating these renewable energy sources with the end users. Either it is storing the thermal energy or storing the renewable electrical energy or any other form. There are many other forms of storing energy. So what is important is now as explained by Srinivas in the morning session, the distribution losses are quite high, more than 20% of the electricity we are losing in the distribution losses as through distribution losses. So in future, what may be interesting is to develop community based energy conversion systems where we integrate the power generation, the air conditioning requirements, the heating requirements, especially for cold countries or in cold weathers, even in northern India, where we need to supply heat energy during the night. So all these multiple energy outputs, either electricity, air conditioning, cooling, cooled air, or heating requirements for cooking or other hot water and other applications, should come as a kind of a community-based energy conversion systems, where a colony may be have a energy supply system where you integrate basically the solar, wind, or biomass, of course depending upon the availability at that particular place, with the storage. You should be able to integrate this and supply it to the local community. Either for an individual house, maintaining a kind of energy integration may be difficult, but community energy supply systems are very common in Western countries nowadays itself. Okay. So that model may save a lot of energy. Means we can use the renewable energy, we can integrate with the end utilization, because the pattern may be different, during the timing and during the days, during the season, the utilization pattern of electricity, air conditioning, and heating requirements are different. Okay, so that is why we need a good storage system, integration for integrating the renewable energies with the end users. Okay, so with that objective, I'm going to present a kind of a already existing integrated energy storage systems, and a special focus to hydrogen, because the hydrogen, everyone started again thinking about hydrogen nowadays. It was there in early 2000s that they saw that hydrogen as a carrier where it integrates the non-renewable or non-renewable energy sources with the end users. But later, the shift has been more towards other renewable energies like solar or wind. But now the people realize that again it is going to play a vital role in the energy spectrum apart from electricity. Of course, electricity is going to play an important role. As of now, the major electricity balance occurs through the grid, because grid itself is a major energy storage kind of system. Okay. But when we want to disintegrate and use more renewable energies locally, then we need to find out the efficient batteries for storing the electrical energy, or we may need to use hydrogen as one of the carrier. Of course, we are there is going to be a larger change in transportation also in the next decade or a couple of decades. We are going to move towards electrical vehicles. The movement has already started, where we are going to use mostly electrical energy based vehicles or electric vehicles or hybrid vehicles, where we combine electrical energy and fuel cells, use hydrogen as a fuel. Okay. So coming back to this, the first topic, the Exergy analysis of the thermodynamic systems. I will try to keep it crisp, because you already learned a lot in the last 3 or 4 days. So the analysis of any thermodynamic system, in fact, any energy conversion system or storage system involves conservative equations. We know that, the first two conservative equations are mass conservation and energy conservation. These two are very simple, straightforward many a times, whether it is a closed system or an open system or a steady flow system, unsteady system. It is easy to write a mass balance or energy balance. We look at the system, try to understand what are the mass inflows and mass outflows, is there any accumulation of the mass within the system. So with that we can write the mass conservation equation. Okay, of course we, in the mechanical point of view, we see that we divide the systems as closed system, open system, and isolated system, and it is easy for us to understand the problem and write the mass balance or energy balance equations, whether it is in rate form or it is in a during a time interval. We can easily write the mass balance equation and energy balance equation. But the problem comes when we want to write the other non-conservative equations. One is the entropy, and the second one is the exergy. Of course, these two equations, because the writing of these two equations for a particular given energy conversion or storage case becomes a bit difficult, because we should have a clarity about what are the energy transactions happening and how to quantify the entropy transfer through these energy transactions. For example, if you take a closed system, we'll have a mass transfer so there won't be any mass transfer through the closed system. There is only energy transfer through the system. And again, in the thermodynamic point of view, especially for mechanical thermodynamic point of view, we see that only for a closed system, the energy transfer can happen only through heat transfer or mass transfer. Okay, of course there may be other things possible, but with respect to this major, with respect to power generation or with respect to the refrigeration, these are the two aspects we look as a mechanical point of view of energy conversion. So we see that for a closed system, the energy transfer can occur either through heat transfer or mass transfer. Sorry, heat transfer or work transfer. Similarly, if you take a open system, we can analyze the open system through a control volume basis. There will be mass transfer through it, and there will be energy interactions with it, and in the form of heat transfer or work transfer. And we would like to quantify this in terms of the entropy also, or in terms of the exergy also. What is the entropy carried by the mass, or what is the entropy carried by heat, or is there any entropy carried by the work transfer because of a pattern of the work, and how to find out the change in entropy during a process, or how to quantify the entropy generation during a process. Okay. If you have a clear understanding of these things, and we can do the entropy balance or even exergy balance very easily for a given case, if you have a clear understanding about how the energy interactions are influencing the entropy or exergy transfer through the system or accumulation within the system, or is there any entropy generation during the process or exergy destroyed during the process. Okay. So I'm going to give a little bit of idea about these processes, may not be in detail, in brief, how to quantify this entropy generated during the process, or how exergy destroyed, how to quantify the exergy destroyed during a process. Ultimately, the second law analysis or exergy analysis ends up with these 2 points only. If in a given case you want to find out, you want to do the exergy analysis or you want to do the second law analysis, you will find, you are interested to find out what is the total entropy generated during the process, and what are it is a function of what parameters that affects the entropy generation. Okay, if you can identify the parameters what are contributing to the entropy generation and find out the effect of each parameter on entropy generation, then we can understand which process is actually contributing more to the more entropy generation or exergy destruction. So we can plan that process in a better way, more idealistic way, okay, so that we can reduce the entropy generation or exergy destruction during the process. That is the ultimate aim of any second law analysis. Okay, so this is shown diagrammatically. These two are the conservative properties, the mass and energy. But whenever there is entropy transfer, there will be some entropy during the process. There will be in any actual process, there will be entropy generation during the process, and there will be exergy destruction during the process. As I told, ultimate aim of the second law or exergy analysis is quantifying this entropy generation or exergy destroyed during the process. As a each process is subdivided into many number of processes. Okay, for example, a fluid is flowing through a heat exchanger. So there the irreversibilities happen, and of course 2 fluids are flowing through a heat exchanger, a hot fluid and a cold fluid, and the heat transfer is happening from the hot fluid to the cold fluid. Okay, so you might have studied already. Professor Brahmara madam might have told you how to quantify the entropy transfer, entropy generation in heat exchange process, because that is one of the topic I have seen there. So here the heat transfer, during this heat transfer, the entropy generation occurs because of the fluid friction, because it is a kind of irreversibility, as the fluid flow is happening because of the pressure difference in the heat exchanger, that will lead to the entropy generation. And whenever the heat transfer happens because of the temperature difference between the hot fluid and cold fluid, that also creates entropy generation. So here a process is happening where heat is transferred from a hot fluid to a cold fluid. So what is our interest is to identify or quantify the entropy generation. Here entropy generation is because of so many subcomponents. Okay, one is because of the heat transfer through finite temperature difference, and because of the pressure drop as the fluid is flowing through the tube. Okay, which is because of the viscosity of the fluid. Okay, so the pressure drop will contribute to the entropy generation or exergy destruction, and similarly the heat transfer will also contribute to the entropy generation or exergy destruction. So we have to subdivide the process into sub processes, and we have to quantify the entropy generated or exergy destroyed through each of the sub process, and we sum up, we will get the total entropy destroyed or exergy, so entropy generated or exergy destroyed during the process. So let me to revise what is entropy, exergy, and how exergy can transfer or how to quantify the exergy destruction during a process, a thermodynamic process. So if you want to quantify that, let us see again what is exergy. Maybe it has different, it may be having different definitions, but we see exergy with respect to the maximum useful work that we can be obtained from a source. So here we are going to quantify exergy in the form of maximum useful work. So in the form of work we are going to quantify, but the work that can be obtained from a system at a state, it is a function of the initial state and the final state. Of course, the path followed by the system while it is undergoing a state change from this initial system to the final system. So since we are talking about the maximum possible work that we can obtain from a source at a particular initial state, the initial state is fixed for the system. We have to find out at its initial state what is the potential to extract work from the system. Okay. So that we can obtain maximum work when only the path followed by the system while it is undergoing from initial state to the final state should be a reversible path, because all irreversible paths will have some kind of irreversibilities which will destroy the exergy during the process. So the path followed by the system should be reversible. That is very important while quantifying the exergy. The second thing is there should not be any imbalances, okay, between the system and surroundings. For example, you are operating the system with respect to a standard environment. Okay? So environment means the conditions at that location, the temperature, pressure, and if, of course, these are the two things we generally consider, but there may be other things, electrical potential or concentration potential. All these things can has the potential to extract work. We have electrical potential or concentration difference or temperature difference between the system and surroundings, pressure difference between the system and surroundings. You have the potential to deliver work. So the system should brought in equilibrium with the thermodynamic equilibrium with the surroundings. Then only we can say that we have obtained the maximum possible, we have extracted the maximum possible work from the system from its initial state. Okay, so the two principles that we have to remember to find out or to quantify the exergy is we have to bring the system through a reversible path from its initial state to the dead state. Dead state is nothing but the environmental state at that conditions, at that place and at that location at that time. So we should be able to bring the system in perfect thermodynamic equilibrium with the environment. Then the work obtained through this reversible path is called exergy. Let us see some of the sources how to calculate the exergy. For example, if you take the kinetic energy or potential energy. So if you take kinetic energy, you take a windmill, we want to generate the electrical energy from the windmill. Okay, so you know the rotor diameter and you know the velocity of air at that location at that particular time. Of course, you have a wind pattern. Based on that, you can roughly calculate the variation of the energy that we can extract in a particular area even before installing the wind turbine there. Okay. So if you want to calculate the exergy associated with the wind, it is nothing but the kinetic energy of the wind. Of course, you ultimately won't get that at the end because of so many reversibilities during this conversion. You have to convert that into rotational motion of the rotor, which is need to be converted connected to the generator and get the electrical energy. There are so many reversibilities in it. But if you see, if you can reversibly bring that wind to the velocity of stagnant condition or to the velocity of the normal condition, so that is the energy that you can produce. Okay, so generally the kinetic energy or the potential energy, which we generally use in case of the hydraulic turbines, the energy itself represents the exergy of the system. Okay, so generally when we define the total energy of the system in the thermodynamic point of view, especially converting thermal energy into work or converting work into a heating or cooling effect, we generally define the total energy of the system. For a closed system, we define it as sum of the internal energy, kinetic energy, and potential energy. Similarly, for a flow system, we define it as because flow system, the total energy, we define it as sum of the enthalpy plus kinetic energy and potential energy. Of course, enthalpy is a sum of the internal energy and the flow energy. Right. So there, whenever we are defining the stream, we generally write these. So because of that, we should know what is the exergy associated with this internal energy, enthalpy, or kinetic energy, or potential energy. So generally, the kinetic energy, potential energy, we can see has the energy itself is the exergy. But whenever it comes to internal energy or enthalpy, because these two are the microscopic forms of energy, not macroscopic forms of energy, not an organized form of energy, the internal energy or enthalpy. Okay. So to make it more organized, which is work is normally a more organized form of energy, to make it organized, we have to spend some energy. Okay, we have to lose some energy. Okay. So that is why the internal energy of the system, or in case of a closed system, especially the enthalpy of, in case of a flowing system, does not represent the exergy of the system. Okay. But whereas the ordered form of energies like kinetic energy or the potential energy straight away represents the exergy of the systems. So whenever we are writing kinetic energy or potential energy in our exergy equations, we straight away take those forms into the exergy equations. We can consider them as itself as exergy. Coming to exergy of a thermal energy reservoir, this you might have heard a lot, in the presentation of Professor Gupta garu. Suppose you have a source at 1200 Kelvin, then here source means, however, that is what we define a thermal energy reservoir whose temperature won't vary by extracting heat from it or by dumping to it. It's a source of infinite heat capacity. For example, if there is a source at 1200 Kelvin and we are extracting 500 kilowatts of energy from it and delivering 180 kilowatts, of course, the remaining 320 kilowatts we are rejecting to the sink. Now I want to find out what is the exergy of this system. Of course, this is the actual system which is developing 180 kilowatts. Okay, so here I did not mention that this is a reversible heat engine. So that means this 180 kilowatt does not represent its exergy. Suppose I replace this engine by a reversible heat engine and find out what is the maximum work that I can obtain reversibly from this energy reservoir, which is at 1200 Kelvin. That represents the exergy of the system. Okay. So if I replace it by a reversible heat engine, we know that reversible heat engine, all reversible heat engines, we can equate it to Carnot heat engine, which is having a efficiency of 1 minus T sink temperature by T source temperature. So if I write 1 minus T sink temperature is 300 and source temperature is 1200. So 300 by 1200 is 1 by 4, 0.25. So 1 minus 0.25, it will have a efficiency of 0.75. So if I take 500 kilowatts of energy, okay, into 0.75, it gives me the work done. So simply if I write the equation in this form, the work is efficiency of the heat input, the efficiency of the reversible heat engine is this. So if I write, it is 0.75 into 500, it is about 375 kilowatts of work I can produce if I utilize this heat energy in a reversible, through a reversible process or through a reversible cycle. Okay, so actual cycle I am getting 180 kilowatts. The reversible cycle, if I perform this, if I perform this, if I do this process in a reverse using a reversible cycle, I am getting 375 kilowatts. Okay, so this difference between these two represents the irreversibility during the process. Okay, 195 kilowatts. That means if I can improve by some means this energy conversion process, the conversion of heat transfer into work, I can save some energy from this 195 kilowatts. Means, there is a chance to store save this much amount of energy. So I have to work on my processes, components, improve them so that at least a part of this can be converted into work. Okay. So this is the irreversibility. That means the maximum possible work that you can get, which is through a reversible process, minus the actual work output you are getting, is the irreversibility in your process. So our aim is through understanding the processes, each process, what is the irreversibility and what are the parameters that are contributing to the irreversibility. And if we can work on them, we can reduce this irreversibility and increase the bring the process more towards the idealistic process, which is a reversible process, which is not possible in actual practice, but we may come nearer to that. So the remaining energy, whatever we do, this 125 kilowatts, what is remaining, if we convert this 500 kilowatts through a reversible process, you are getting 375 kilowatts of work. The remaining 125 kilowatts need to be rejected to the environment. Whatever you do, this is called unavailable energy. So whatever we do, we can't do anything with this part of the unavailable energy. It has to be rejected. Okay. So only thing is this 195, we can work on it and we can reduce it so that we can increase the energy, the work that can be obtained from this system. Let us take a finite heat source, how we can deal with the Exergy calculations of a finite heat source. This is easy because the temperature is not varying. So whenever the heat transfer is happening at a particular constant temperature, the heat transfer itself is a reversible process. Okay, see to make heat transfer reversible, the only criteria we look for is the heat transfer should happen at a constant temperature. That is a major criteria. Okay, so suppose if the heat source is not of finite heat capacity, let us take, I have a block of iron which is at 200 degrees centigrade. Okay, the room temperature is 27 degrees centigrade. So I can say that the energy, it has some thermal energy by virtue of temperature difference between iron block and the surroundings, which is room. So this thermal energy, I want to find out the exergy involved with this thermal energy. Okay. So simply if you transfer this heat, okay, for example, the iron block is of 200 kgs. Simply if you transfer this heat, okay, then the process won't become a reversible process, because as the heat transfer is happening, the iron block temperature keeps on reducing and ultimately it reaches 27 degrees centigrade when the equilibrium is achieved. Okay, so this process won't be a reversible process. To find out the exergy of this block, I have to conduct the heat transfer process in a reversible manner. But how to conduct the heat transfer process in a reversible manner? So for example, for that I take a number of reversible heat engines which are connected in series. Of course, it is very theoretical way of doing the things. Practically, it is not possible. But the exergy by definition is bringing the system from its initial state to the final state, which is the environmental conditions, through a reversible process. So to find out the exergy of this block, now all the heat transfer, intermittent heat transfers, whatever the heat transfer is happening, I have to conduct it through a series of reversible engines. For example, at 200 degrees centigrade, it transfers some heat. Then I bring one more reversible heat engine at 199 degrees centigrade. Again, it transfers some heat. Okay, so the process I am dividing into a number of processes, at each step the temperature is remaining constant during the heat transfer, so that we can visualize the process as a reversible process. So instead of doing at a stage, I am calculating what is the reversible work that can be obtained when it is operating at a constant temperature. Of course, this temperature is varying as it is cooling from 200 to 27 degrees centigrade. So instead of considering as a single process, I am dividing this process into n number of small processes. In each small process, the temperature is remaining constant through the heat transfer. For example, here I am considering 173 processes. So at each 173 processes, the temperature is constant. Okay. So now each process I am treating total 173 processes. Each process I am treating as a reversible process. So in one step, we can obtain a reversible work when the temperature remains constant, is given by the efficiency of the reversible heat engine operating between at that temperature and the environment, and the heat transfer during that small interval of step. So now if you want to find out the total reversible work that can be obtained as the iron block is cooling from 200 degrees centigrade to 27 degrees centigrade, we have to integrate this. Okay. So we have to integrate this. Again, for integrating this, we need the help of the first law of thermodynamics to find out this delta Q out. What is this delta Q out? Okay. So if you take this as a closed system, the energy entering minus energy leaving the system should be equal to change in energy of the system. Of course, there is no energy entering the system. The energy is leaving in the form of heat transfer. So this is negative. The delta E out is delta Q out, which is leaving the system, which is must be equal to, since it is a closed system, we know that the sum of the total energy of a closed system is sum of the internal energy, change in internal energy plus change in kinetic energy and change in potential energy. Here, since it is considered as a stationary closed system, we can neglect the change in kinetic energy and change in potential energy. So the change in internal energy can be written as simply mCV delta T, which is we are relating with respect to its specific heat. Okay. Since now we got the expression for, since Q in is equal to Q out, there is no Q in. Q in is to the reversible heat engine, which is nothing but Q out from this system. Okay. So equating this Q out is equal to Q in here. Of course, this is then we can obtain the heat that is transferred to the system to the reversible heat engine in each step. Okay. So we can integrate this easily. Now we can find out the exergy of the system. So this gives the maximum reversible work that can be obtained. Suppose here we have taken 500 kgs of the iron block. So it can give now 8,191 kilojoules of the work. Suppose, let us take one more case study. I am taking this thermal energy to just to heat a room and to keep it at 27 degrees centigrade at during a winter session where the outside temperature is 5 degrees centigrade. So what can be the maximum thermal energy that we can supply to the room? At one instant, it looks like that. Of course, mCp delta T is the energy that we can transfer without doing anything. Okay, but that, as I told, that is not a reversible process. That is a irreversible process as the heat transfer is happening because of the temperature difference. Okay, so to make it away again, this is a reversible process to find out what is the maximum possible heat that we can transfer to the room. Now we have to, so this is the actual heat that we can transfer without doing anything. So from as the room is losing heat to the surroundings because of this temperature difference of 27 degrees centigrade and 5 degrees centigrade, the same we have to provide that heat to keep the temperature of the room constant at 27 degrees centigrade. Okay, so what is the maximum at instantaneously? We can see that it is 38,000 kilojoules or nearly 39,000 kilojoules that can be supplied to the room by simply rejecting heat from this 500 kgs iron block keeping in the room to the room air. But that does not show the maximum energy that it can be transferred to the room. To find out the maximum energy that can be transferred to the room, we have to conduct this process in a reversible manner. So to conduct that process in a reversible manner, we have to run a reversible heat pump, okay, heat pump which is again working on a reverse Carnot cycle, and use this work energy which we obtain from a reversible heat engine to run that. Okay, so when we are using this work to run the reversible heat pump, okay, so we can calculate the heat pump when the heat pump is operating between 5 degrees centigrade and 27 degrees centigrade. We can find out the COP of the heat pump. From that we can calculate what is the energy that can be rejected by the heat pump to the room. So from the heat pump we can reject this much amount of heat to the room. But that is not the end of the story, because the heat pump also rejects the the difference is rejected, because the heat engine rejects this much difference of heat into the room. Okay, so when you are using simultaneously a reversible heat engine or a reversible heat pump in combination to utilize this thermal energy from the iron block to supply thermal energy to the room to keep it warm, the total energy supplied by it is the energy rejected by the heat pump and the energy rejected by the heat engine, this combination of these two. That means you can supply nearly 4 times the actual energy, thermal energy present in it. Okay, that is 1,42,000. But this is not practically possible. Okay, but it gives a maximum limit how you can do the process if you conduct everything in a reversible manner. Okay, so you are developing using this thermal energy in a reversible manner to develop the work. That work you are using in a reversible manner to pump heat from a lower temperature body to a high temperature body. In that case, if you do everything reversibly, what is the potential available to it? So it gives you a maximum limit for the thermal energy transfer. Of course, this we are not calling it as Exergy, because Exergy we are defining with respect to the work only as a pure definition. But if you see what is the potential for this iron block to transfer heat to the room to keep it warm at 27 degrees centigrade, when the surroundings is at 5 degrees centigrade, is almost 4 times the actual energy it present with respect to that environment. So that shows the maximum potential for a source to transfer heat as in the form of a heat, the energy that can be transferred in the form of a heat. So using this definition, we can easily derive the expressions for the energy of a exergy of a closed system or exergy of a open system. So for example, to define exergy of a closed system, let us take a fixed mass which is there in a kind of a piston cylinder assembly. It is a very general example, very frequently we consider in case of in teaching thermodynamics, right? So let us take, we have a gas which is at a higher pressure and temperature compared to the surroundings. The surrounding pressure is P0, the surrounding temperature is T0. Okay, so now we know that to find out the exergy of this closed mass, we have to bring this mass in equilibrium with the surroundings, that is P0 and T0, through a reversible process. Okay, so here generally the boundary work happens very slowly. The boundary work we consider it as a reversible work in the absence of the friction between the piston and cylinder. Okay, so we can find out what is the work done by this gas on the atmosphere, okay, or on this load, that is the load we are connecting, as its pressure is reducing from P to P0. Okay, so that is one useful work that we are going to obtain by deducting the work done by this piston on the atmosphere, that is the work done on the surroundings. The other aspect is, while we are bringing the temperature of the system from T to T0, while bringing the temperature of the system from T to T0, how much work we can reversibly obtain? That is what we have discussed in the earlier case. By running a series of reversible heat engines, we are trying to bring down the temperature from T to T0 instead of bringing it at once, because we need to conduct the heat transfer each time at a constant temperature. Okay. So we are using a series of reversible heat engines to obtain a reversible work from as the system temperature is reducing from initial temperature T to T0. Okay. So we have to find out what is this reversible heating work that we can obtain while its temperature is we are bringing from initial state T to T0, and similarly what is the work that we can obtain as its pressure is reduced from P to P0. So for that, again, we have to start with the energy balance. If we start with the energy balance, it is a closed system. We write the total energy entering the system minus total energy leaving the system should be equal to change in energy of the system. Okay. So if you see there is no form of energy entering into the system, but the energy is leaving in the form of work transfer because of the PdV work, and the energy is leaving because of the heat transfer to the surroundings through a heat engine. Okay, so we write both are leaving the heat transfer through a reversible heat engine, and the work done on the piston, that is the load connected to the piston, should be equal to, since it is a stationary system, the total change in stationary energy, total energy change in stationary system is given by the change in internal energy of the system. Now, what we have to do is we have to find out what is the reversible work out of this, and out of this delta Q, what is the reversible work we can obtain. To find out this reversible work, this is the PdV work. So I am deducting the work done on the atmosphere, and of course I am also adding the work done on the atmosphere to make equate it to PdV. Okay, so this P minus P naught is nothing but the useful work that I can obtain as the piston is expanding, because it is acting against the atmosphere and doing some work on the atmosphere, plus P naught dV. Of course, this is equal to the PdV. These two terms becomes equal to the PdV. Similarly, if I run a reversible heat engine using this delta Q, I can produce delta WHE minus T naught into ds. That is the work that I can produce. So if I substitute delta Q here and delta W here and rearrange for my the total useful work through this heat transfer as well as through this reversible work done, I will get the expression for the Exergy. I'm sorry. Yeah, I will get the useful expression for my Exergy. So this is the how I got the Exergy, the expression for the Exergy. Of course, this is well defined. The formula we can easily remember also, but how it comes, is very important, because if there is an unknown situation, you should have a clarity on how to bring this system to the in equilibrium with the dead state, that is the conditions of the environment, through a reversible process. If you know this concept, you can easily calculate Exergy of any system. Okay. Of course, it is a bulk mechanical work. The work itself represents the Exergy of the system. If there are no dissipative effects during the delivery of the work, as work we are seeing, so don't see that work that is we are delivering, because when the work is there that we are delivering for a particular purpose, it undergoes so many forms, and there will be losses while you are converting into one form into another form. Okay, for example, if you are converting electrical energy in thermodynamic point of view, especially when we are doing thermodynamic point of view analysis, we treat electrical energy also as work. Okay, so when we are converting into shaft work, there will be losses. Okay, so don't say that the electrical work, the shaft work we are getting from electrical energy, shaft work itself it represents the Exergy. No, the electrical energy represents the work, but during this conversion from electrical energy to the shaft work, there will be losses because of the as you are moving a kind of a motor there will be dissipative effects, there will be losses. Okay. So that clarity we should have, but as if work itself, you see that itself represents the Exergy of the system, but not the other forms of energy, like internal energy is a form of energy we discuss, and enthalpy is also a form of energy. That does not require, because those are all microscopic states of the energies. Okay, so when you come to flow system, I don't want to take too much time here, because the only difference between the closed system and the flow system is the flow energy that we have already discussed. Because the flow energy is represented by PV, it also need to do some work on the atmosphere to push out the gases into the atmosphere or to come into the system. So we are deducting that atmospheric energy spent to come out of the system. So if we add that X flow to the Exergy of the closed system, then we will get the Exergy of the open system. Okay, that means a steady flow process. Okay, a flowing stream. What is the Exergy of the flowing stream? Okay, that is given by this expression. Of course, to find out the Exergy change during a process, we have to calculate the Exergy at the initial state, Exergy at the final state, and if you deduct 1 from 2 or 2 from 1, you will get only the difference, because the environment being same at state 1 and 2, you will simply get H2 minus H1 minus T naught into S2 minus S1 plus V2 square minus V1 square by 2 plus Z into Z2 minus Z1. Okay, so that gives the entropy change during a process, either for a steady flow stream. Okay, or for a closed system, it simply becomes U2 minus U1 minus T naught into S2 minus S1 plus change in kinetic exergy of the kinetic energy and potential energy. So most of the times, if it is not significant, we can easily neglect the change in exergy due to kinetic energy and potential energy, and we are interested in change in exergy only due to the internal energy and the enthalpy. Okay. The other thing is how to write the expression for exergy and how to quantify it, exergy destruction. Okay, so only through we have already learned a lot. Only through reversible process, there won't be any exergy destruction. Okay, the exergy remains constant if the process is a reversible process. But if it is any actual process, there will be some exergy loss during the process. How to quantify it? For that, you take an isolated system. Why I am calling it as an isolated system is, if you take any system, any isolated system, or you take a system and it's on the influence on which it is felt, a process undergone by the system is felt, the system and surroundings put together, we can call it as an isolated system. Okay, so system, a process where in which the system is occurring and where its effect is felt on the surroundings. If you both together, a process effect is felt only in system and surroundings. The other, that is the immediate surrounding of the system, the other surroundings are not unaffected. So the system and surroundings together, we can call it as an isolated system, because the other system, no energy transfer or no mass transfer has happened other than the system and surrounding. Okay, so that itself we can call it as an isolated system. So it is a virtual one. There is no complete and isolated system. It is very difficult to define a completely isolated system, but we can define the isolated system by considering the system and surrounding on which the process effect were felt. So that's how I am considering an isolated system. If you write even for exergy balance, we have to start with the energy balance only. We can derive the exergy balance from the energy balance only, whatever the case may be. So I'm starting with the energy balance. Since an isolated system, E in minus E out is equal to delta E of the system, because since it is an isolated system, there won't be energy entering into the system or energy leaving the system. Okay, so the energy of the system constant, that means delta E of the system is equal to 0. And if I write entropy balance, of course I have not dealt about the entropy balance, I will come back again to that. So if I write the entropy balance, the entropy transfer can happen through mass transfer, through heat transfer. Of course, the energy work generally does not carry any form of entropy, but work conversion will carry entropy. Work itself does not carry the entropy. So if you see that, then for an isolated system, entropy, there is no mass entering, no energy entering, either in the form of heat transfer or work transfer. So the energy and entropy entering is 0 and entropy leaving is 0. So the change in entropy of the system should be equal to the entropy generated during the process. So these two equations I got for one process that is happening in the isolated system by energy balance as well as by the entropy balance. Okay. So now I just modify this process. I multiply this equation T naught, so it becomes T naught S gen equal to T naught into S2 minus S1. Now I deduct 2 from 1, so I get the equation like this. The rearranging T naught S gen is equal to, if RHS, if I take U2 minus E1 minus T naught into S2 minus S1. Okay, and we see, because for a closed system, isolated system is an extension of the closed system. If you see an isolated closed system, the exergy change is given by this. Okay, so the exergy, because here there is no change in volume, it is considering as a fixed volume system. So the exergy change of a closed system can be written as, here in this case also there is no change in volume, it becomes E2 minus E1 minus T naught into S2 minus S1. So this represents the exergy change. This term represents the exergy change of the isolated system, because isolated system is a case of the closed system. Okay, that's why I have taken this closed system. And now, because there is no change in volume of the system, I'm equating this, because this is basically the work done because of the movement of the change in the volume. Okay, so that I am deducting it. So this represents the exergy change of an isolated system during a process. That means as a process occurs and an isolated system undergoes a state change from 1 to 2, so this represents the exergy of the final system minus the exergy of the initial isolated system should be equal to minus T naught Sgen. So that indicates that the exergy of the final system is always less than the exergy of the initial system, because this can never be, this term can never be negative. Okay, so this term is positive because this is the absolute entropy, and whenever an actual process happens, the entropy generated is 0. So that we can easily understand from the entropy balance or entropy, the principles of the entropy, which I have not discussed here. So that indicates that the exergy of a system always reduces whenever a process happens. The end exergy will always be less than the exergy at the beginning. So the exergy difference, whether it is a reversible process, for a reversible process, of course, S generation becomes 0. For any actual process, this becomes the exergy of a process reduces during the process, which can be again quantified from by quantifying the entropy generated during the process. So to quantify the exergy destroyed during the process, it is very important to quantify the entropy generated during the process, which can be done by doing the energy entropy balance. So again, this is the entropy balance, because the either entropy can enter the system or leave the system. In case of a closed system, the entropy can enter only through the form of heat transfer, because the work transfer does not carry any entropy with it. And in case of the open system, either the entropy can transfer in the form of mass transfer or the heat transfer. Okay, so if you do the energy balance, entropy balance, so the entropy transfer by heat transfer, of course, this is strictly it is del Q by T. As I told, the heat transfer need not happen at constant temperature. Then we divide that into a number of small, infinitely small processes, where we can assume that the heat transfer during each infinitely small process is happening at a constant temperature. That's how we can calculate the entropy transfer. And entropy, because of the work transfer, it is 0, because it is ordered form of energy, the work transfer, and entropy transfer by ms, no, through the mass. So we can use this to quantify the entropy generated during the process generally. Okay, so we need to know what is the entropy of the system at the initial state, entropy of the system at the final state, and the entropy generated through during the system we can quantify. But here the important is we need the properties of the entropy at the initial state, at the final state. Of course, we need to quantify the entropy entering the system or leaving the system. Of course, the entropy transferred through the system can be quantified by thermodynamic relations again. Okay. But to find out the entropy at the initial state and final state, you should know what is the entropy of the medium. For example, steam, the steam properties are available, or R134A you take, the properties are available. If it is an unknown substance, then we have to derive this entropy as a function of different other properties. So that we can do using the property relations only. That's why we study property relations in thermodynamics, which has very, very important role. How different properties are related to each other in a single substance. Okay, or how the properties are related to each other whenever a process happens. At a particular state, how the properties are related is given by your equation of state. Okay, so either you can use ideal gas equation of state or real gas equation of state with some modifications to the ideal gas equation of state. But during a process, how to relate the different properties, that comes through your the relation between the properties, that we generally call it as Maxwell relations. So Maxwell relations, we get a relation between, especially for entropy change as a function of pressure, volume, and temperature. These are the measurable quantities. So by doing experiments, by measuring the change in pressure and volume and temperature during the process, we can relate the non-measurable quantities like entropy change. First, you can get through Maxwell relations, which you can further use to quantify the change in internal energy or enthalpy as a function of this entropy change or other properties. Then you can get the change in internal energy and enthalpy, and you can formulate the tables. That is how the formal tables are formulated. Of course, again, how to take the reference state. Whenever you are formulating these tables, thermodynamic tables, the reference state always you should assume. Okay, so in thermodynamics, we won't absolutely speak about these analysis, energy conversion cycles or energy storage while using the properties or taking these properties and calculating the energy change during a process. these are not absolute values, whatever we are substituting the values. So these are with reference to the some reference state which is always constant. Okay, so the change in properties is always saying whatever may be the reference state. So reference state is arbitrary. The delta S you are calculating, delta U you are calculating, and delta H is calculating is same. Okay, because these are obtaining, we are obtaining through a thermodynamic relation irrespective of the reference state. Of course, this property data is very much required. If it is not available to you, you have to choose a reference state and use the correct thermodynamic relations, the equation of state and the property, the equation of process to calculate this change in entropy or entropy at a particular state with respect to some reference value. Okay, so this S2, S1 should be with respect to a common reference state. Then only you can calculate S2, S1 correctly. Okay. So now you have the property data S, and you quantify the entropy entering or leaving the process. Then you can easily quantify the entropy generated during the process. Okay. So once you know the entropy generated, you can do the Exergy balance and you can quantify the Exergy balance. Of course, Exergy transfer happens through all mass transfer, heat transfer, and work transfer. Of course, by knowing the heat transfer Q quantity, you can calculate the Exergy transfer as. So this is the Exergy balance equation. It is a very simple equation again. Whatever may be the process, whatever may be the fluid, the total Exergy entered during the process minus the total Exergy leaving during the process minus Exergy destroyed during the process should be equal to change in Exergy of the system. Of course, for a closed system and open system, of course, Exergy destroyed can be calculated by using this or quantifying the entropy generated during the process. Okay, so Exergy transfer by heat transfer. As I told, the heat transfer, we can quantify Exergy transfer as 1 minus T naught by T into Q. As I told, the heat transfer need not happen at a constant temperature, but in that case, we divide the total process into a number of small processes and then we integrate it to find out the total Exergy with respect to the heat transfer. And similarly, we can quantify the Exergy transfer by work. Simply, that is work in case of when no boundary work is involved, that is work done on the surroundings. If there is a work done on the surroundings during the process, then we have to deduct that from the work done, so we can obtain the reversible work done during the process. Okay. So of course, each mass will carry some Exergy with that. It has internal energy. Each mass has some internal energy. With flow energy, it gives the total Exergy carried by the mass with it. So doing this, we can easily do the Exergy balance for the closed system and open system. In case of a closed system, there is no the mass Exergy carried by the mass because there is no mass transfer. The Exergy carried is only because of the heat transfer as well as work transfer. And we typically taking here that the heat is transferred to the system and work is done by the system. So we are taking the heat transfer as the Exergy entering into the system and the work that is leaving as the work leaving the system. So this is a general notation of the power generation systems. Otherwise, it can be anything. The heat work can enter the system and heat can transfer the system. So if you write the general notation, it never goes wrong. Whenever we are doing Exergy balance for any energy conversion process, the Exergy entering minus Exergy leaving minus Exergy destroyed should be equal to the change in Exergy of the system. Okay, so that is the best way of generally starting the Exergy equation. Okay, so for control volume, apart from that, the Exergy transfer because of the energy interactions in the form of heat transfer or in the form of work, we also have the Exergy transfer because of the mass transfer. So we sum it up like this. For example, if you take a case where some mass is entering the system, mass is leaving the system, and heat is transferred to the system and work is done by the system, and the Exergy equation sums up into like this, because this is the Exergy is entering in the form of heat and it is leaving in the form of work, so E in minus E out. And similarly, the Exergy entering because of mass, if there are multiple mass flows into the system, minus the Exergy leaving through multiple mass flows from the system, minus Exergy destroyed should be equal to the change in Exergy of the system. So as I told in the beginning of the lecture, we need to quantify the Exergy transfers, the initial Exergy of the system and final Exergy of the system. simply to calculate, the important way is to quantify the Exergy destroyed system. Okay, so this Exergy destroyed is through a multiple sub processes and through multiple parameters. So we have to identify, quantify the Exergy destroyed through each of the sub process and sub parameters, and we need to work on it to reduce the Exergy destruction during the process. For example, if you want to do, sorry, I'm rushing a bit at the end. The Exergy balance, if you want to do for the ideal power cycles, okay. So ideal power cycles means it can be the power generation cycles like your steam turbine cycle, Rankine cycle, or Breton cycle, or Otto cycle, diesel cycle, UL cycle, or these are all ideal cycles because we are assuming so many assumptions are there while we analyze the power systems using these cycles. We are assuming a particular fluid, air as which is an ideal gas as the working fluid. Then we are neglecting so many reversibilities during the cycle, and we are doing it. Okay, but nevertheless, it gives a benchmark for the Exergy destroyed. That is the minimum Exergy that is destroyed during a cycle. Okay, for example, you take a closed loop cycle. It can be any cycle, as I told. It can be your Otto cycle. It can be your diesel cycle, or it can be Rankine cycle or Breton cycle. Okay, so the Exergy destroyed, the general equation we start from T naught into Sgen. Of course, we are not considering here the Exergy entering and Exergy. Everything comes out through the generation term, entropy generation term. So entropy generation, now from entropy balance equation we can write that, because we know entropy balance is S, entropy entering minus entropy leaving should be plus entropy generated should be equal to change in entropy of the system. So I have taken the all other terms except entropy generated to the right hand side, so it becomes like this: the entropy change of the system minus entropy entering plus entropy leaving the system. For example, if you take any closed loop cycle, because in the cycle the system is brought back to its initial state. Okay, so the final state and initial state are same in case of a closed loop cycle. Okay, so this term becomes 0. So it simply becomes T naught into the entropy transferred in and entropy transferred out minus entropy transferred in, because minus T naught we have to write. So here as I told, if it is a very idealistic way of approach, we take that the entropy, the heat transfer is happening from a constant temperature, and heat rejection is also happening to a constant temperature sink. In that case, we can quantify the Exergy destroyed very easily by using Q by out, Q out by Q T at what temperature. If in actual cases it won't happen at constant temperature, then we have to integrate as a function of temperature to find out the entropy generated thereby the Exergy destroyed during the process. For example, if you want to do a individual component in this cycle, for example, if you want to do it for a turbine, a compressor, it simply varies. Okay, you have to consider for a open system. Okay, so open system you have to write the entropy generation term. You have to write the expansion of the entropy generation term. Okay, so this is how we can do the entropy balance, either or Exergy balance, either for any ideal cycle or a actual cycle, or a ideal process or steady flow process, or the actual process. So let me to take an example and already calculated Exergy destructions in a combined power generation system. Okay, so here I have taken a integrated power system for a community. So this analysis was done by Abraham Dinser. He has a lot of books on Exergy, especially for power generation systems and cold storage systems. Unfortunately, I started working yesterday only just to check the availability of the system. Since this is not my direct research topic area, I have started searching for some books where I can take the reference and take out some quantitative values about the Exergy. So last night I searched, there are many books available from this author. Abraham Binzer is a professor in Ontario University at Canada, okay, on power generation or even for cooling systems or a combined systems. Okay, so this is one of the paper from his book where the solar, wind, and the biomass are integrated together for sending the the electrical energy and heating and cooling requirements of about 50 houses in Canada. This is the case study done at practical system at Canada, which is about for 50 houses, in each house having 4 persons. So about roughly 200 persons the energy is supplied. Okay, so they have the some solar panels, especially thermal panels, okay, where you can harness the solar thermal energy, and they have a wind turbine installed, which is of 60 meters footer diameter, and they have the biomass system which operates on this municipal solid waste. Okay, so they have integrated this solar energy, of course, is integrated with the space heating system, especially in cold weathers. They require a lot of the heating requirements. During summers, they may be requiring cold, that is produced through a absorption chiller. I'm sorry, absorption refrigeration system. Using that, the cold output is produced, and of course, an organic Rankine cycle is used to produce the power. And from wind turbine and the gasifier, they're directly getting the electrical energy. Of course, they are using a gas turbine in combination with the fuel, which is generally the methane-rich fuel, which is obtained by digestion of the municipal solid waste. Of course, the solid leftover works as a manure. It's a rich in humus manure, which is very good for the organic cultivation. So both this electrical generation from the wind turbine and anaerobic generation are coupled through a electrical energy storage system, that is through battery to the load. Okay, so the load is nothing but your the domestic electrical energy requirements. Okay, so now they have done the energy balance and the Exergy balance for the practical system, and the Exergy balance is given like this for solar thermal system. Only for the thermal harnessing, for solar plates itself, there is a Exergy destruction of this is total solar system Exergy destruction of 70,000 kilowatts, which is again divided among the different system, because Rankine cycle has the highest the Exergy destruction, because of the, especially in the turbine as well as in the condenser, the Exergy destructions are more. A lot of Exergy destruction they have observed. And the wind turbine, the losses in the bearings and the structure, the stress obtained by the structure, all these things are contributing to the Exergy destruction. So this shows the solar subsystem where the different Exergies are presented in the different subsystems, especially the Rankine cycle. This is the Rankine cycle where the steam generated from the solar collectors is used for producing the power. Okay, so there is a lot of Exergy destruction in the turbine, and next one comes the condenser in case of the Rankine cycle. Of course, in steam generator, because of the heat losses, the Exergy destruction is happening. In the turbine, there is irreversibilities associated with the expansion process, as well as the heat transfer. Heat losses during the turbine are contributing to the Exergy destruction. And here a majority of the heat you are rejecting to the environment without utilizing it. So that heat loss is contributing to the Exergy destruction in case of the condenser. So this is a absorption plant where a typical vapor absorption system, you have a evaporator where cooling is produced, which is used for the air conditioning applications. Then that is absorbed by a ammonia water system in the absorber, that is pumped to the generator, and ammonia is separated here in the generator. okay, by supplying the hot energy, hot fluid through it. Then this evaporated ammonia is condensed in a condenser to produce back the liquid ammonia, which is again evaporates to produce the cooling. So the exergy associated with this generator is huge in this case of the ammonia separation process. Okay. So they have quantified the different exergy destructions in the each of the subsystems. Like this is a solar subsystem. Similarly, they have the wind and the biomass subsystems. Of course, the equations used are very similar. The solar subsystem, the heat loss from the solar panels, the heat gained from the solar insolation with respect to the ambient temperature and the sun temperature gives the exergy available in the solar panels. So there is a lot of exergy destroyed during the harnessing of the solar energy itself, because only a very fraction of the solar energy is converted into the thermal energy. Okay. Then the exergy associated with the wind can be calculated directly from the wind velocity and the rotor diameter of the blade. The exergy associated with the biomass is calculated using the mass of the actual biomass obtained from the municipal waste. Okay. Then having approximate chemical formula of the chemical that biomass separated from the chemical waste, and based on the methane produced from it. Of course, from the calorific value of the exergy associated with the methane from the can be calculated from the calorific value by knowing the heat that can be obtained, the thermal energy that can be obtained from the biomass. So that can be used to calculate the exergy. So that you can calculate exergy efficiency, which is exergy extended because of the electrical energy supplied, because exergy extended is the exergy available at the output. In this case, there are multiple outputs. The output is the electrical load taken by at the domestic usage, and the exergy associated with the cooling of the rooms during for air conditioning requirements, or themselves, or the heat.
Hello, sir. Hello, sir. Can you hear me? Right. Dear participants, kindly wait. I think there is network issue on our expert side.
Dear participants, sorry for the inconvenience. Participants are requested to wait for a few minutes. There is some technical issue from the presenter side. So participants are requested to wait. Don't leave the meeting.
Yes, sir. You can proceed, sir. Kindly, sir. Your volume is not audible, sir.
Sorry, I lost the connection. Just a minute.
Yes, yes, sir. Yes. Kindly, sir.
I need to share the presentation, or is it visible?
Uh,
I think I need to share.
Yes, yes.
Yeah, sorry. Yeah. So we can study a lot of parameters, the effect of so many parameters like this. Okay. So some of the other systems, I would like to bring to your notice is integration of using hydrogen as an integration for the other renewable or sources. For example, here they have proposed, of course, second line analysis has not been done for this system. They have proposed a ORC driven generator that is using the solar energy, organic Rankine cycle. They are developing the electrical energy, which they are using hydrogen as a storage, for balancing the electrical load. So whenever they have the excess energy, they will send it to the electrolyzer, using which you can produce the hydrogen, which is stored in a tank and which is supplied to the fuel. And it is not supplied continuously. Whenever there is less availability of the solar energy, especially in the night times, then you can supply the hydrogen to the fuel cell, and it can supply back the control volume, supply back the electrical energy requirements. Okay, so that is how we can do the, instead of using a battery, this is how we can do the load balancing using the solar energy, or even for the wind energy. But the major challenge here is the cost of the electrolyzer and fuel cell. One thing is, if you are using batteries for grid level applications, you might be requiring a few storage of the batteries, a few multi-storied buildings as batteries. So this for grid level applications, large level applications, this seems to be a good option for intermediate energy storage. But the cost is people are working on still electrolyzer and fuel cell costs. If we can divide this into a single device, okay, just like reversing of your compressor and turbine, one way it works as a turbine, the other way it works as a compressor, so that the system becomes more reliable. Because batteries, again, it has a life. The energy storage densities, efficiencies are less with respect to batteries. But this, once installed, this will have a larger life, of a few decades life it will have, and the efficiencies involved are quite high here in case of the intermediate energy storage. The major challenge again is storing the hydrogen. Again, hydrogen can be stored in a compressed state, compressed gaseous state, or liquid state, or a solid state. Of course, a lot of research is going on in this also. Compressed gas, you require a lot of energy to compress it and store it, because electrolyzer generally produces hydrogen at ambient conditions. Okay, and you want to use a particular volume for storing hydrogen, you need to store it, develop cylinders which can withstand very high pressures of the order of 700 bar. Then you have to compress it to such high pressures. However, for fuel cell vehicles, as of now, the compressed hydrogen is being used for carrying the hydrogen along with the vehicle at 700 bars. Of course, we are also working on how to compress hydrogen to such high pressures using low-grade thermal energy. So this is one way of storing the energy. So of course, this is the expansion version of that scheme, where you have a compound parabolic concentrators receives the solar energy using a thermomechanical energy storage. As an intermediate thing, you produce the organic Rankine cycle, then integrate that with the the power inverter or controller, because the fuel cell need to be integrated with the power demand. Then the organic Rankine cycle, you supply the energy to produce hydrogen, which is using the electrolyzer, which is you are producing the hydrogen, which is stored in a metal hydride form here. They already developed the system where they use the solid state hydrogen storage, the metal hydride system. That is a separate topic. The uses of metal hydrides for handling hydrogen, especially for storage, then compressing it, or developing some energy conversion systems, or for thermal energy storage. That's a separate topic where I can talk in a length 2 to 3 hours on the topic. I try to put it here, but because of the time constraints, I don't want to go into details of that. Okay, but the energy integration is possible with these kind of systems, where either it is electrical, the wind-based energy systems, or solar-based energy systems. So instead of batteries, the hydrogen can come into play as a intermediate energy carrier or storage system. So what I will do is I will go to the almost towards the end of the presentation, because if I want to talk about the other systems based on hydrogen, it will take another 1.5 hours to 2 hours. So this is how the future energy spectrum is going to look like. Initially, we have seen that it is majorly the fossil fuel energy based system, but in future we have to implement the carbon capture. Okay, we have to remove the carbon dioxide or carbon monoxide from the exhaust gases before we release them into environment. So even we use fossil fuels, we have to implement the carbon capture to eliminate the carbon dioxide or carbon monoxide. Or from these primary energy sources, we produce electricity or hydrogen. We use the combination electricity and hydrogen for different applications, either for transportation or for domestic applications, or producing cooling or heating also. And finally, the total energy spectrum becomes sustainable because we are taking water and releasing oxygen into the environment, and again we are taking oxygen from the environment, releasing water to it when we are using the hydrogen as the end product. So the overall spectrum looks sustainable when we are using especially renewable energies like solar, wind for the different energy applications, energy requirements. So I'll stop here. I'm sorry if there is some kind of discontinuity between the
Nothing, sir. Nothing.
explanations. Yeah. Though I have covered majorly the introductory part again, I hope at least it will be useful to some of the audience.
Yes. Dear participants, if you have any queries, you can interact with sir.
Sir, I think there are no queries.
Yeah. I think I'm a bit late because your lunch also got delayed because of that.
No reason. Thank you, sir. Thank you, Dr. Anil Kumar, sir. It was a wonderful session on energy analysis of thermodynamic system. I hope participants would have understood every concept you have taught us. It was a wonderful session. Thank you so much, sir. Thank you for your participation.
Thank you. Thank you. It is nice interacting with you. Yeah, I am also gaining knowledge by listening to other sessions. Of course, I could not listen much. Today's, at least Srinath's session, I got some points from his talk. Thank you and all the best for your future programs.
Thank you, sir. I met you in Vijayawada, sir.
Oh, you met me in Vijayawada. Okay.
Yeah, along with the Dr. V.V. Reddy, sir.
Yeah, one conference.
Yes.
2012.
Yes, sir. Right.
At that time, I was working with IIT Indore.
Yes, sir. Indo. Now you have switched over. Congrats, sir. Thanks a lot, sir.
Thank you. Thank you, sir.
Announcement for the participants. I request the participant to leave for the lunch and be ready with the session 3 which will be started at 2:25. So participants can leave for the lunch and join at 2:25. Thank you.